Okay, so we had talked a little bit about where specific electrons live last week. We're going to get a whole lot more specific with it as we get into actual electron configuration. It stopped recording for some reason and kicked me out. Okay, so something that you may have already picked up on, every orbital can hold 2 electrons. There's no orbital that can hold more than 2 electrons. The maximum capacity of any orbital is 2 electrons. No matter what energy level, no matter what orientation, no matter what shape, an orbital can hold 2 electrons. So how many electrons can be held in a single orbital? 2. How many electrons can be held in a 4d3 orbital? 2. How many electrons can we hold in a 1s orbital? 2. 2, 2, 2, 2, 2. Just 2. Never more, never less. Not 3, not 1, 4 is right out. 2 electrons in each orbital. Now, this makes it possible for us to do something really cool. On that first main energy level, how many shapes are possible? What do we have on the first main energy level? 1. 1. And it's our old friend, the beach ball, the 1s. So we have 1 shape possible. On the second main energy level, how many shapes are possible? How many shapes? 2. So we have our beach balls, and we add to that our drumsticks, or our dumbbells, or whatever we're calling them. So we have 2 shapes. On the third main energy level, how many shapes are possible? 3. We have the beach ball, and we have the dumbbell, and we have the double dumbbell. 3 shapes. Huh. If you were a betting person, how many shapes would you bet are there on the fourth main energy level? 4, and you'd be right. And how many do you think there would be on the fifth main energy level? 5. And what do you think there would be on the sixth? 6. The number of shapes possible is equal to n. Okay? Because remember, n is the main energy level. So the number of shapes possible is always equal to the same number as the energy level. So on your test, I will ask you a question like, how many shapes are possible on the 7th main energy level? How many? Yeah, 7. How many shapes are possible on the 4th main energy level? I'll ask you that question, and you have to know that n is equal to 1. And you have to know that n is the main energy level. Okay, so let's talk about the specific number of actual orbitals. So on the first main energy level, remember, if there's more than one orientation, it has to be represented. How many actual s orbitals are there on the first main energy level? How many ways can you orient a beach ball? Just 1. So we only have 1 orbital. On the second main energy level, we've got the s and the p. How many actual orbitals are there? We have 1 s, because there's only one way to orient it. How many p's do we have? 3. So we've got, so how many is that? 4 actual orbitals. Okay, well on the third main energy level, we have 1s, we have our 3 p's, we're up to 4. How many d's do we have? 5, so 4 plus 5 is what? How many orbitals do we have here? 9. Anybody see any patterns so far? N squared is the actual number of orbitals. So how many orbitals would you expect to find on the 4th main energy level? 16. What about the 5th main energy level? 25. 7th main energy level? 42? 49. I always screw that one up too. Yeah, so the number of actual individual orbitals is just the main energy level squared. Okay, so let me ask you this. How many electrons can an orbital hold? 2. If you can hold 2 electrons in an orbital and you have 1 orbital, how many total electrons are on that energy level? 2. Good. You can do this. Okay. Well, if you've got 4 orbitals and they can each hold 2, how many electrons are on the second energy level? 8. If you've got 9 orbitals and they can each hold 2, how many electrons are possible on the third energy level? 18. And if you've got 16 orbitals and they can each hold 2, how many electrons could you hold there? 32. And what about the fifth main energy level? How many electrons could be held there? 50. What's the pattern? If you had to write that algebraically, what would you write? Jot it down. Okay, fine, it's in the notes, but not everybody figured that out. Not everybody reads the notes as we're talking. 2n squared. So I will ask you a question like, how many electrons are possible on the third main energy level? And you have to go, oh, okay, well, n squared, 9 times 2, 18. Okay, pretty easy. Now, we've got a lot of electrons here, and somebody in the other class said, well, if 1s can hold 2 electrons, how do you show hydrogen? Ah, good question. Not all of these spaces are filled up. You know, if I hold one thing in each hand, I can hold 2 things. Do I have to hold 2 things? No, I can hold one thing, I can hold no things. Woohoo! Look, Ma, no hands. You know, so you don't have to have an electron in every spot where you could. Okay. Let's pause. And this is just an example of what we just did, so we can do one more. If we're on the third, well, no, let's do the fourth, because we did the third as an example. So, fourth main energy level. How many shapes? 4 shapes. How many orbitals? 16 orbitals. How many electrons? 32 electrons. Possible. Doesn't mean that they'll be there, but that's how many are possible. Okay, so now we're going to start to talk about electron configuration. This is the pattern of electron orbital filling that an atom undergoes. We can look at any atom, look at how many electrons it's got, and figure out where they are, where they're located, where they should be located or could be located. That's its electron configuration. And everything about how that atom bonds, doesn't bond, reacts, doesn't react is all based on its electron configuration. So the pattern of its electrons completely governs how stable or how reactive something is. This is nice because there are just rules. And if you just follow the rules, you get it right. It's very formulaic. It doesn't require a whole lot of higher thought. So it's kind of a nice little break from things that have required higher thought. Like, if you follow the rules and you plug everything in, you get the right answer. Woo! Now, how do we figure out how many electrons an atom has? So, 2 pieces of information that you typically have about an atom or about an element: atomic number and atomic mass, right? Which one of those is going to help you figure out how many electrons you've got? Okay, how many of you would say atomic number? How many of you would say atomic mass? Good. Yeah, it's atomic number. What does the atomic number tell us? How many protons there are? Well, in a neutral atom, what's the relationship between the number of protons and the number of electrons? They're equal. So whatever the atomic number is, that's how many electrons we're starting off with. And this is before they lose or gain or we do any kind of funky stuff with charging them. Okay? So once we know how many electrons something has, we can figure out where to put them. Okay, the first rule is called the Aufbau principle. It's German. Lots of the particle physicists were German, though Aufbau doesn't translate particularly well, so we're not going to bother with that. Aufbau just says that an electron is going to go into the lowest energy orbital possible. Okay? It is going to take the lowest energy spot available to it. Now, this is pretty logical. We just have to know which ones are lower in energy. And It's really easy to start with. 1s, then 2s, then 2p, then 3s, and then things start to get a little weird. But before we get into the weirdness, the metaphor that I typically use for this is to imagine, and many of you are going to go off to college either this fall or maybe next year, and many of you will occupy buildings that have high-rise dormitories, and some of those high-rise dormitories will have multiple rooms on each floor, and when you show up loaded with your suitcase, your refrigerator, your microwave, your pet hamster, all of your clothes and your books and your God knows what else you're going to drag along with you. If there's no elevator, you really don't want to walk up any more stairs than you have to. So if there is a room available on this first floor, you're going to snag it. So you don't have to carry it all up the stairs. Okay? You're not going to go to the second floor if you don't have to. And if the first floor is filled up, you're not going to jump to the fourth floor. You're going to go to the second floor because, again, you don't want to climb any more stairs than you have to. Okay? So that's really all that Aufbau says. What the heck is that? Something that you're going to learn to draw. You may want to get it tattooed on your inner arm. I don't know. I don't know what you want to do with it. This diagram, which you are going to create for yourself repeatedly, and you'll actually get 2 points on your test just for being able to draw it. It's an easy 2 points. This shows the order in which the orbitals fill. It shows their order of increasing energy, though it's flipped on its head. So we'll go ahead and recreate this together ourselves. Everything starts off with 1s. It's the lowest energy orbital there is. And then there's a 2s, because of course every orbital has a 2s. And then on the second main energy level, there's also a p. Well, what we know is that if the main energy level below you has that, you have it too. So we can go ahead and fill this all the way down to the bottom on the s's. And on the p's, 3p, 4p, 5p, 6p, 7p. And then starting on the third main energy level, we add a new orbital subshell. What is it? 3d. Okay. And then, of course, we've got d's all the way down. 5d, 6d, 7d. Well, on the fourth, we add another one. What do we add? F. So we have 4f, 5f, 6f, 7f. And in theory, we could go out into the 5G, 6G, but you know what? In practice, we really never do. This is about as far out as anybody ever draws this, and a lot of people don't even include some of these lower orbitals. You'll see why in a second. So then, if we take a straight line, and we run a straight line through these like that, we fill 1s first. This shows us the order in which these fill. 2s, 2p, then 3s. Okay, we haven't had any real surprises yet, right? We all knew that we were going to fill 3s after 2p. Well, the next line, if we draw it like this, seems to say that we're filling 4s before 3d. Eh? Oh. It's true. It's a little ugly. It's a little weird. You'll get over it. So we fill 3p, then we fill 4s, and now it just, I'm going to say, all chaos breaks loose. Because we fill 3d, then we fill 4p, then we fill 5s. Cats and dogs living in sin. I don't know, all kinds of craziness, madness. It's not that bad. And then after 5s, we fill 4d, and then we fill 5p, and then we fill 6s, and then, if we're really lucky, we get all the way up to 4s. So that's the orbital subshell filling diagram. You will learn to draw this on your own and draw the lines through. And the first couple times you might screw up the lines. That's a really common problem people have. They do something weird and their lines don't go where they're supposed to. So I would actually practice it. And I think there's a question on the chapter review that I'll give you that's just draw the orbital subshell filling diagram. That's this. And I will ask you on your test and on your quiz. Okay. So using this, we can figure out what subshell fills after the last one. We can figure out the order in which they fill. Great, but that's still not enough to get us an actual electron configuration. Okay, so that's a graphic looking at how you can have lower energy on the 4s than on the 3D. May or may not be helpful, so if you want to just kind of learn, love, live this and forget about thinking about why, you have my blessing. That's the first rule. Let's go on to the second rule. Okay, so the second rule is called the Pauli exclusion principle. It's named for Wolfgang Pauli, another German particle physicist and generally interesting guy. And this is where we get that address idea. We talked about specifying addresses for electrons. All Pauli exclusion says is each electron has to have its own address. So in a single orbital, remember every orbital can hold how many? 2, just 2. One is going to be designated spin up. One is going to be designated spin down. That's all that Pauli exclusion says. And you pretty much already knew that, but we have to make sure that we remember that. Okay, so Hund's rule says if you have 3 orbitals that have the same amount of energy, before any of them have 2 electrons in them, they're each going to get 1 electron. And you can think about this in terms of the dorm room. If you're coming in with your whole load of stuff and there's only 1 person in the room on the first floor, you know, you'll double up with them. You'll take a roommate rather than having to climb to the second floor. Or maybe you wouldn't, but an electron would. You're, you know, highly valuing your privacy. So on the 2s is slightly lower energy than 2p. So on 2s, once there's 1 in 2s, you can put a second one in. In 2p, remember, there are actually 3 separate orbitals. So if you get up to that 2p level, and there is 1 electron in the first orbital, it's not going to take a roommate until every single room there, every single orbital, has an electron in it. So the filling is going to look something, here, let me get rid of the label 2p. You're going to get 1 there. Well, nobody's going to double up until they have to. 1 there and 1 there before you start to see doubles. So then, once there is somebody in each room, then we start to see 2 electrons per orbital, but not until then. Okay, let's actually just go ahead and see what this means. All right, so using those 3 rules, we are going to learn to write electron configuration 3 different ways. And the first one that we're going to do, this is the longest and the most cumbersome. Every single thing we do from here will be a way to shortcut it. So we're going to learn the longhand first, and then we'll just keep shortcutting it until you get down to the shortest possible notation. So this is called orbital notation. It's called orbital notation because we actually draw each and every single individual orbital. Ooh, it's okay. So let's imagine carbon. Carbon's got how many electrons? You got a periodic table handy? Carbon has 6 electrons. So we're going to actually draw the orbitals, and what we do is we just write the name of the orbital and we put a little line over top of it, and that's where we're going to draw our electrons. So we have 1s, then we have 2s, Then we have 2px, 2py, and 2pz. 1, 2, 3. Once we draw one orbital for a subshell, we have to draw them all. Okay, you have to do that. So we have 6 electrons, 1 electron, 2 electrons. So far, so good. Where is the next electron going to go? Where? 2s. Okay. Where's the next electron going to go after that? Where? 2s. Yeah. So we're up to 4 electrons. We have 2 more to place. Where's the next electron going to go? Somebody who has shoelaces. Lots of you have shoelaces. Well, we said, where does the next electron go? Do we have any in 2p? No. Because those are their own energy levels. That shell. Okay. Right, right. Good question. Okay, so now we've got 1 in 2px. Where does the next one go? 2py. And then that's it. We're done. Okay, let's try one that has 9 electrons. What would that be? Fluorine. Oh, yeah, okay. Oh, good one. Okay, so we're going to draw our orbitals. 1s, 2s, 2px, 2py, 2pz. Where does our first electron go? 1s. And 1s is the lowest energy orbital possible, so once 1s is doubled up, then we can move to the next energy level. So the lowest energy orbital on the second energy level is 2s. So we're going to put 1, 2 electrons there. Where does the next one go? 2px. And the next one? 2py. And the next one? 2pz. Now what? 2px, 2py. And we're done. Okay? Not too bad. Okay, if we have something with 12 electrons, this is what, magnesium? Oh, good. Hey, look at that. Woo-hoo. Okay, so we're going to draw our orbitals. 1s, 2s, 2px, 2py, 2pz, 3s, 3px, 3py, 3pz. Okay, first 2 electrons go where? You can make little sound effects if it makes you feel better while you draw these. Next 2 go. Now, you know perfectly good and well that you're going to fill the 2p subshell, right? I'm going to beg you, even though you know that, to still go, okay? Get in the habit of going all the way through the subshell, filling in 1, and then doubling them up. You know you're going to fill it, but I beg you, develop good habits. Okay, so we're up to what? 2, 4, 6, 8, 10. Where do our next 2 go? Oh, this is, yeah. Where do our next 2 go? 3s. 1, 2. Okay, we didn't even need to draw the whole 3p subshell. Whoops. There. Okay, so that was pretty easy. Let's draw your orbitals. 1s, 2s, 2px, 2py, 2pz, 3s, 3px, 3py, 3pz. Okay. What do we do with the first 2? Next 2? the next 6. I just like making sound effects. So we're up to 2, 4, 6, 8, 10. 5 to go. Where do the next 2 go? 3s. And then we have, so we're up to 12, we have 3 to go. Yep, 1, 2, 3. It's not hard. It's not hard at all. It only gets weird when we get up after 3p. Do you want to do one that's after 3p? Okay, Kaylee, it's your time to shine. What happens after the 3p's? So I'm going to just do this. Five s, 6s, 2p, 3p, 4p, 5p, 6, yeah. 3D, 4D, 5D, 6D, and that'll get us far enough. Oops. Okay, so after 3p, we go to 4s, and then what? Then we go to 3D. So you have to follow the line. So 1s, 2s, 2p, 3s, 3p, 4s, 3d. So remember we have how many d orbitals? 5. So we have 3d1, 3d2, 3d3. I'm going to have to shrink those. Let's point out a couple of things. So 1s. That is a subshell. It's the 1s subshell. It's also an individual orbital. 2s is an orbital and a subshell. This whole block of 3 is a subshell. Okay? 3s is its own subshell. 3p is a subshell. 4s is a subshell. Okay, 3D is a subshell. Now, we could do some pretty color coding and say, okay, well, and that's a main energy level, and this plus this is another main energy level, and of course 4 will go with its own thing, but we're not getting there yet. Here's the rule. If you draw one orbital from a subshell, you have to draw them all, even if there's only one electron in that whole subshell. If we have one lonely, sad little electron in the 3D subshell, you still have to draw 3D1, 3D2, 3D3, 3D4, 3D5. So let's start counting. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. That would be the orbital notation for cobalt. Okay. You'll have lots of opportunities to practice. I'll get the homework assignment for the chapter review up on the board today, and you'll have lots of chances to practice. Tomorrow, we'll continue with this. We'll learn the second form of notation, and I'll give you a FIP quiz. Or maybe I'll give you a FIP quiz over just this. We'll see. We'll see how it goes.